Hi everyone, so hope you're all doing well. And if you're new to the channel, my channel is called A-Level Maths Tutor UK. So I'm a YouTube channel that goes through the A-Level math syllabus and some extra tips and useful information as well for A-Level students. So before we actually go ahead and do any maths in this video, I just want to just make a few points. So if you are new to the channel or if you are already a subscriber, please do like the video. Please do click the like button. It really does help out the channel. It really does. Please click like now. Please also do subscribe to the channel as well. Again, it just really helps the algorithm out. And please do share as well to year 12 students. So this video is going to be about hypothesis testing, and it's going to be an introduction to hypothesis testing. So please do share this with any year 12 students you know, or just share it around so that year 12 students can see this video, because hypothesis testing is a very important topic in A-level maths, and it's a topic that a lot of students struggle with. So that's why I'd like to that's why I'm kind of requesting that you all share this video as much as possible. So thank you very much. So let's now get into the video. So as the title says, and as I've just said now, this video is going to be basically an introduction to hypothesis testing. So I know in the title I've called it a dummies guide to hypothesis testing. But really, this is just going to be a very slow, step-by-step introduction to hypothesis testing. So again, it's a topic that a lot of students struggle with in A-level maths, especially the first time that they see it. So I've done this presentation here to try and give you a step-by-step intuitive guide as to what hypothesis testing is and how it works. So this video specifically is going to be about hypothesis testing with the binomial distribution. I'm going to do a video in the future on hypothesis testing with the normal distribution. But today's video is going to be an introduction to hypothesis testing with the binomial distribution. So only watch this video if you've seen the binomial distribution. If you've not seen the binomial distribution yet, if you've not studied that in class yet, or you've not seen that at all, please don't watch this video yet, because I'm going to assume that you've seen the binomial distribution. So we need to know the binomial distribution before we can do any hypothesis testing. So please do make sure you are aware of what the binomial distribution is, and then we can go ahead with this video. So this video, again, a step-by-step guide to hypothesis testing. So it will be quite long, but I'm going to go very slowly, going to take it step by step. So, feel free to pause the video at any time and come back to it, another time when you're free, because it's going to be quite a long video. But it will be a step-by-step introduction to hypothesis testing and what it's all about. So I guess the best way to explain hypothesis testing is to go through an example. So let's say you live in a town, and let's say someone says to you that 80% of people in your town have brown eyes. So, again, you live in a town and there's some kind of fact, some kind of fact that's going around that 80% of people in your town have brown eyes. So let's just assume that is true. But you've got this suspicion that it's actually different from 80%. So again, someone said to you, 80% of people in this town have brown eyes, but you've been around town, it's your hometown, you've walked around town, and you know a lot of people. Your suspicion is that 80% of people is not the correct statistic. So that's what you think. And you're a very curious human being, you're a very curious person. So you want to investigate whether the percentage of people in your town really is 80%. Okay, so yeah, what you're going to do, you're going to put the theories to the test. So we've got two theories here, two hypotheses, right? So we've got this hypothesis here that the percentage of brown-eyed people in your town is 80%. And then you've got this kind of alternative belief that actually, or this alternative suspicion that 80% is not the right number and it's something different. So it's either 80% or it's not 80%. So that's kind of what we want to do. We want to put the theories to the test. And, how are we going to put the theories to the test? We're going to collect data, right? That's the whole point. We're going to collect data. And yeah, so we're putting, as I just said in this kind of bullet point here, we're going to put the theories to the test. And hence we call this a hypothesis test. So we're testing two beliefs, we're testing two hypotheses. Yeah, so you've got a hypothesis. Someone suggested that the percentage of brown-eyed people in your town is 80%. And then you've got this other hypothesis, this alternative kind of hypothesis, that it's not 80%. So we're going to collect some data and we're going to see which hypothesis is more likely to be true. That's the idea of a quote hypothesis test. Okay, so we're going to test the theories. That's what we want to do. So obviously it's unrealistic that you're going to, ask everyone in your hometown the color of their eyes. I mean, if you've got, if you live in a town with 50,000 people, um, you're not going to be able to go to every 50,000 people in your town and investigate what color eyes they have. I mean, it's just not practical and you're not going to be able to do it. So what do statisticians do and what are you going to do? You're going to take a sample, and what you're going to do is you're going to take a random sample. So it's quite important that this is a random sample. Obviously, you could just ask the first 50 people that you see walking down the street, or the first 100 people, how many people you want to take in your sample. But we want this for the purposes of the A-level maths course. We want the sample to be random. So remember what a random sample is. A random sample is a sample where every single person in the population has an equal chance of being selected in the sample. So again, let's say you've got a town of 50,000 people. A random sample would be a sample out of those 50,000 people where every single one of those 50,000 people has an equal chance of being involved in your sample. That's a random sample. Now, walking down the street and picking the first 100 people you see to take part in your survey, that's not a random sample. That would be a bias sample, because not everyone in your town is going to have an equal chance of being selected. Because if you're not, on the same street as you, then you've got no chance of being selected in your sample. So a random sample could be, for example, you've got a list of all the 50,000 people that live in your town, and you're going to give every one of those 50,000 people a number, and then you use a random number generator to generate, let's say, 100 numbers. And those 100 numbers that you generate correspond to the 100 people that will be in your sample. So for the purposes of A-level maths, we want to make sure the sample's random. In real life, I mean, it's maybe not practical to do a properly random sample, because maybe you don't have the names of everyone that lives in your hometown. So again, practically speaking, your sample in real life might not be random, but the purposes of A-level maths, it's going to be a random sample, and you'll see why soon in this presentation. You'll see why it's got to be random. The sample size that you choose is arbitrary, so you decide that. So it could be 50 people, 100 people. You'll take a sample size, a sample size that you think is a good sample size. Again, in theory, the bigger the sample size, the better. But you'll take a sample. So let's take a sample of 100 people. Okay, let's choose 100 people. So we've got, again, 50,000 people, 100,000 people in the town, but we're going to take a sample of 100 people because obviously we can't interview everyone. So the first question is, okay, so we're going to take 100 people. That's what we're going to do. What are we going to ask them? Are we interested in their heights? Are we interested in how big their eyes are? Are we interested in like yeah, I don't know, anything you like? Are we interested in, what time did you wake up in the morning? What are we interested in recording? We're interested in recording, do you have brown eyes or not? So it's a binary option, isn't it? So you either have brown eyes or you don't. That's what we're interested in. And what statistic are we interested in? So a statistic is just a piece of data. What piece of data are we interested in this investigation? Well, it's the number of people who have brown eyes out of 100. Okay, so remember what we're testing. Someone thinks the percentage of people in your town that have brown eyes is 80%. You don't think that. You think it's something different. So what if we're going to do this investigation, if we're going to investigate the percentage of people in your town who have brown eyes, then we're interested in the number of people in your town who have brown eyes, obviously. So we want to count out of 100 people, how many of those 100 people in your sample have brown eyes. We're going to count. So we're going to count the number of people who have brown eyes, and then we're going to compare that with 80%. Okay, so the original suspicion was that 80% of people have brown eyes. So if that's true, we would expect 80 people out of 100 to have brown eyes. But as we just said, we're going to take a sample of 100. We will count how many of those people have brown eyes. We're going to count the number, and we will compare it with 80%. We'll compare it with 80. That's kind of the idea. So this is called the test statistic in this case. So you'll probably see, if you're doing, obviously all you guys be doing A-level maths, you may hear this term test statistic. So the test statistic is just the statistic, it's hard to say, the statistic that we're interested in. So in this case, we're interested in the number of people out of our sample of 100 people who have brown eyes. That is called a test statistic. When you do hypothesis tests, so in year 13, you'll do hypothesis tests with something called the normal distribution. You'll be interested in the mean. So maybe like the mean height of people in your sample, the mean time it takes for people in your sample to run 100 meters. So the test statistic will be different depending on the distribution you're working with. But with these hypothesis tests, and a hypothesis test where we're interested in the percentage of people who have a certain characteristic, the test statistic will just be the number out of your sample size. So with this hypothesis test, the test statistic is the number of people in your sample who have brown eyes. That's our test statistic. You don't really need to worry too much about this in A-level maths because you don't really use this term test statistic too much, but just be aware we call this a test statistic. Okay, so let's recap the two hypotheses. So the key thing in A-level maths and also in university maths and statistics is you have two hypotheses. You have what we call an original or status quo hypothesis. And in this case, this is what we supposed before, that the percentage of people in the town with brown eyes is 80%. Right, so that was the original belief. That was the status quo belief. That was the original hypothesis before we had any suspicion that it may be different. Okay, that was our original idea. And the technical term for this is called a null hypothesis. Okay, it's called a null. So in stats, we call this a null hypothesis. So the null hypothesis is something equals something. So the percentage of brown-eyed people in the town is 80%, or it could be the average height of people in your town is 10 centimeters, right? Whatever it may be, right? A null hypothesis is always something equals a number, equals a percentage, equals a probability, right? That is the original belief. So originally, before we did this investigation, we thought, or it was people thought, some people thought that the percentage of people in your town with brown eyes was 80%. That's called a null hypothesis. That's the original hypothesis before we do any investigation. And also, this is a key point as well. So we assume that this null hypothesis H0, and again, this is notation, the notation is H0 for a null hypothesis. We assume that this H0 hypothesis is true before and once we collect the data. So when we do the investigation, we have to assume it's true because that was the statistic that we were told to start with, okay? So common sense, we just have to assume that's true until our data may suggest otherwise. So our second hypothesis was this new alternative theory, this new alternative hypothesis, and that was the hypothesis that you suppose. So your suspicion was that actually, having gone around town, the percentage of people in your town with brown eyes is not 80%, so not equal to 80%. So this was your alternative theory, your new theory, and we call this in statistics the alternative hypothesis. So you have a null hypothesis, which is the percentage equals something, and you have an alternative hypothesis, which is the percentage is different from, sorry, let me go back. The percentage is different from the percentage you thought before. Now, as I'll come on to in a minute, you could have an alternative hypothesis, which is something like the percentage of brown-eyed people in your town is less than 80%, or the percentage of brown-eyed people in your town is greater than 80%. So there's three different types of alternative hypotheses you may have. You may have a less than, a not equal to, or a greater than. But again, we'll come on to this in more detail in a minute. But for the purposes of this example, the alternative hypothesis is that the percentage of brown-eyed people in the town is not equal to. But in theory, it could be bigger than, it could be less than, depends on what our suspicion is. depends on what your suspicion is, depends on what the suspicion is of the person in the question of the exam question that you're answering. But in this case, we'll just say not equal to 80%. Okay, so let's again just go for a bit more notes on, you know, these hypotheses. So again, as I said before, it's always H0 versus H1. So you've got two hypotheses. It's always hypothesis, null hypothesis versus alternative hypothesis. So that's how we do these tests in statistics. It's always H0 versus H1, two hypotheses. So as I said just now, so H0 is always something equals a number. So it could be the probability of people in your town having brown eyes is 80%, something equals something. As I said before, when you do normal distribution in year 13, you'll see normal distribution hypothesis tests where you do hypothesis tests about the mean of a population. So like the mean height of people in a population. And that would be, so your null hypothesis in that case would be your mean equals a number. So it's always equal. So the null hypothesis is always something equals something, okay? So in our example, our null hypothesis, H0 would be P equals 0.8. So the probability or the proportion percentage of people in the town with brown eyes, 0.8. So we normally use P as in probability with these hypothesis tests, or P for proportion. That's normally what we do. So then our alternative hypothesis could be, again, as I was saying before, you've got three options. So it could be something is not equal to something. So something is not equal to a number. So like the one that I just showed you on the previous slide, we said P was not equal to, the proportion was not equal to 80%, not equal to 0.8. So that would be called a two-tailed test. So again, another technical term. When you have an alternative hypothesis where the proportion is not equal to a number, or the mean is not equal to a number, or some quantity is not equal to a number, we call that a two-tailed test. And the reason why it's called a two-tailed test is because with this type of hypothesis test, where we've got this type of hypothesis where something does not equal something, in theory, the something in the asterisks here, the asterisks, could be less than that number or bigger than. So two options, it could be less than or bigger than, two-tailed test. Now, when you've got hypotheses like this, so something is less than a number, sorry, an alternative hypothesis like this, so when something is less than a number, or when something is bigger than a number, we call this a one-tailed test. So these two examples here are called one-tailed tests because we're not, with these tests here, we're only looking whether, we're only investigating whether a number is less than, sorry, a quantity is less than a certain number, or whether a quantity is bigger than a certain number. So we're only looking at one tail of the distribution of numbers, if that kind of makes sense. Hopefully that this is making sense a little bit. So we call, so if we've got an alternative hypothesis where something does not equal a number, we call this a two-tailed hypothesis test. When we have an alternative hypothesis where this quantity, this proportion, or this mean is less than a number or bigger than a number, we call it a one-tailed hypothesis test. Again, just some technical terms to be aware of because we're going to use these two terms in the presentation. So again, going back to the example in our, this presentation. So our example, because you have this suspicion that in your town, the proportion was not equal to 80%. In our hypothesis test, the null hypothesis is the proportion is not equal to 80%, not equal to a 0.8 probability. So this would be a two-tailed test. Now, again, if you had a suspicion that the probability of if the probability of brown-eyed people in your town was less than 80%, this now becomes a one-tailed test. Also, if you had a suspicion that the proportion of people in your town who are brown-eyed was bigger than 80%, again, we would call that a one-tailed test. But in this example, your suspicion is that the probability is not 0.8. We call this a two-tailed test because there are two possible outcomes, two possible options. the proportion could be either less than 0.8 or it could be bigger than 0.8. So we call this a two-tailed test. But again, in probability, in statistics, you'll have one-tailed test and two-tailed test. This example is a two-tailed test. Okay, so again, something to be aware of. When we'll come on to this in more detail soon, but once we collect our data and make a conclusion as to whether whether we go with our null hypothesis, our null theory, or our alternative hypothesis, our alternative theory, be aware that in our conclusions in exams, we write accept H0 or reject H0. So the reason for this is because when we do the investigation, as I said on the previous slide, actually, let me go back to the previous slide. So when we got, was it on this slide here? Yes, here, this bullet point here. So when we go into the investigation, when we go to collect our data, we assume that this H0, this proportion here is true when we go into the investigation. So when we collect our data will either support this theory we had before, this original theory of 80% of people in the town having brown eyes, or it will not support that theory. So the wording, we've got to be careful of the wording of our conclusion. When we make the conclusion from our data, we're either going to accept the original theory or reject the original theory. So we're not going to accept or reject the alternative theory because we assume going into the investigation that the original theory is true. So if you assume that the original theory is true and you collect data based on that original theory, your data will either support your original theory or reject your original theory. So we just got to be careful with the wording of our conclusions. But again, we'll come on to this in more detail. Don't worry if you're getting a bit confused now. Again, we'll come on to this in more detail soon. So this slide here is just what we said before, one-tailed versus two-tailed test. This example is a two-tailed test. Okay, so let's think about what results we could get. So again, remember, we got a sample of 100 people in our town. We're going to collect a random sample, 100 people in our town, and we're going to collect and we're going to count. We're interested in counting how many of those 100 people have brown eyes. That's the whole point of this investigation. So what if we counted 80 people out of 100 who had brown eyes? So remember, our null hypothesis, our original kind of status quo assumption that we had to go into the investigation assuming was that 80% of people in the town had brown eyes. So what if just we took our sample of 100 people and 80 people exactly had brown eyes? Well, I mean, that's pretty bang on it. Well, it is bang on, isn't it? So, before the investigation, there was this, suspicion that 80% of people in the town had brown eyes. You've just gone and collected your data and you found out that bang on 80% of people in your sample have brown eyes. Then it seems like this original hypothesis, so this H0, this null hypothesis, is a very good shout. I mean, let's be really careful here because it does not prove that the null hypothesis is true. In statistics, when you collect data, you can't prove a hypothesis is true. But if there was this suspicion amongst people in the town that 80% of people in the town have brown eyes, you've collected a sample of 100 people, 80 of those 100 people had brown eyes, 80% of those people. Well, this kind of original belief that 80% of the people in the town have brown eyes seems like a good shout. Seems like a very good shout. So that's something that we could get. Now, what if we get 0 people in the town having brown eyes? So again, we're going to get our sample of 100 people, our random sample, and we find out that none of those people have brown eyes. Right, so none of these people have brown eyes. We thought it was 80%, but actually our sample, our data, out of those 100 people, none of those people have brown eyes. So is this null hypothesis of 80% good? Or actually, should we go with the alternative hypothesis, this H1? Yes, I mean, it would suggest that H0 isn't true. Again, it doesn't prove it. We can't prove, collecting data doesn't prove anything, but it would suggest that H0 is not true. So it would suggest that the proportion of people in the town is not 80%. It would suggest that the proportion of the people in town, I'll just repeat myself, sorry. It would suggest that the proportion of people in the town who have brown eyes is not 80%. So it would suggest that H1, the alternative, your new belief, so your new belief that you came up with, your suspicion, your new suspicion is true. It would suggest that. It doesn't prove it, it would suggest that. So what if we get, again, 100 people out of 100 people with brown eyes? So again, we've collected our sample of 100 people. Every single one of those people had brown eyes. Do we go with H0 80% true? Or do we go with H1 80% not true? So remember, H0 is 80% is the true number. H1, our alternative belief, your suspicion, your new suspicion. Remember, H1, your alternative hypothesis, is your suspicion, your new suspicion, right? Again, if you're getting 100 out of 100 people with brown eyes, it's probably not true that 80% of people in your town have brown eyes. Again, can't prove it. We're collecting data and we're making inferences based on data. So this is why this is called inferential statistics. You're making inferences based on data, okay? So you collect your data, 100 out of 100 people have brown eyes. The null hypothesis, the original theory was that 80% of people in the town have brown eyes. You've got 100 out of 100 with brown eyes. It would suggest that H0 probably isn't true, and it would suggest that 80% is probably not the true number. Again, not proving anything. Now, this is where it gets a little bit interesting. So what if you collect your data, you got your sample of 100 people, and you find out that maybe 70 of those people have brown eyes, or maybe 90, or maybe like 75, or maybe 85 people have brown eyes. So close to 80, close to 80%, but we get 70 or 75 or 85 or 90, those kind of numbers. So not quite 80, but not like a million miles away. So what do we say in this case? I mean, does this suggest that our H1 is true? Does it suggest that H1 is not true? Does it suggest that 80% of people in the town have brown eyes? Does it not suggest that? I mean, how do we tell? I mean, how can we tell whether 70 people having brown eyes in our sample of 100 people is good enough to keep our percentage of 80%, or whether it's good enough to say, actually, do you know what? 80% is probably not the true number, and 70 out of 100 people having brown eyes may suggest that 80% is not the correct number, so we go with H1 as our hypothesis. So how do we tell that? I mean, where is the cutoff point? I mean, what potential numbers out of our 100 people would we actually turn around and say, okay, we go with H1, or okay, we don't go with H0, we go with H1, or okay, we stick with H0 and don't go with H1. So where is the cutoff point? Where do we go with that? So what we could do, and this is perfectly fine if you're a statistician, if you want to do this, if it's it's your investigation at the end of the day, there's no rules to say how you do your investigation. You could just say, well, I mean, again, we've got this sample of 100 people. You could just turn around and say, well, okay, well, let's say we got anything between 0 to 70 people with brown eyes, or 90 to 100 people with brown eyes. Then let's just say, do you know what? It's too far away from 80 people. We're going to reject H0 if we get between 0 and 70 people with brown eyes, or 90 to 100 people with brown eyes. So let me just explain that again, just to be really clear about it. So our H0 is our null hypothesis. And that was the original status quo, original belief that people thought in the town, that 80% of people in the town have brown eyes. So as a statistician, you could just turn around and say, okay, I'm going to collect the data. I'm going to get my sample of 100 people. And let's just say if we get anything below 70 people with brown eyes out of those 100, or if we get anything above 90, I'm going to reject that hypothesis. I'm going to reject the fact that the proportion of people in the town with brown eyes is 80%, and I'm going to go the alternative. Okay, you could just decide that arbitrarily, your choice as a statistician, you could decide that. So let's go ahead and let's just go with the flow with this. Let's just say, okay, we're going to get our sample 100 people. We're going to count the number of brown-eyed people. If we got 65 brown-eyed people, then we reject H0, we reject the initial suspicion. Or if we get 91 people with brown eyes, we reject the initial suspicion. But if we get, let's say, 89 people with brown eyes, then we would keep the null hypothesis. We would have to keep assuming that the people, that the proportion of people in the town with brown eyes is 80%. Okay, so that's how we're going to do our investigation. Let's just say that's the way we're going to do our investigation because we decided to. So again, this is kind of what I'm saying here. So out of our sample of 100 people, right? So we collect our 100 people. We're going to ask them, do you have brown eyes? If none of those people have brown eyes, or 1, or 2, or 3, or 4, or 5, 6, 7, 8, 9, all the way up to 70, or 90, or 91, 92, 93, 94, 95, 96, 97, 98, 99, 100 people. If we collect our 100 people and we record a number, any of those numbers out of the 100 who have brown eyes, then we would reject the idea that 80% of people in the town have brown eyes. So we would reject H0, that null hypothesis that 80% of people in the town have brown eyes. And why? Okay, so why? Because we chose to. Okay, so as the statistician, you decided that to be the case. There's no mathematical reason why we did this. We're just saying, okay, in our investigation, let's just do this. Let's just say any of these numbers here, we're going to reject H0 for these numbers here. Okay, no scientific reason why we've done this, but let's just go with the flow and say this is what we're going to do. Okay, so we call this set of numbers here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 70. And then 70, then 90. So we're forgetting all the numbers between 70 and 90. We're jumping straight to 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. So we call this set of numbers the critical region. Okay. So we've decided that out of 100 people, if we record 0, 1, 2, 3, all the way up to 70, 90, 91, all the way up to 100 people with brown eyes, we would reject H0. So the set of numbers or the set of potential test statistic values we could obtain that would lead us to reject H0 is called the critical region. And in this case, we chose the critical region. So in our test here, we chose it. Okay. We decided that this set of numbers here would be our critical region. So that's what a critical region is. This term here is very important in hypothesis testing, critical region. So again, the critical region is the set of potential test statistic values we could obtain that would lead us to the conclusion of rejecting H0. Okay, that's what a critical region is. So it's a set of potential numbers we could get from our sample, the set of numbers we could count in our sample that would lead us to reject H0. And in this test that we came up with today on the spot here, we chose that region. We chose these numbers. Okay, and that's perfectly fine. We could do that. There's no rule saying we can't do that. We can do that. So again, just to be really clear, in our example, 0, 1, 2, 3, 4, 5, all the way up to 69, 70, and then jump to 90, 91, all the way up to 100, is called the critical region. So we use curly brackets in maths to denote a set of numbers. Okay, so the set of numbers 0, 1, 2, 3, 4, 5, up to 69, 70, and then 90, 91, all the way up to 100 is called the critical region. Now, these numbers that we've missed out in between 70 and 90, so 71, 72, 73, all the way up to 89, this is called our acceptance region. So again, if we collect the data, so we got a sample of 100 people, and let's say we count 72 of those people with brown eyes, that means we would accept H0 because it's not in the critical region. Okay, so 72 is pretty close to 80. So in our test that we've designed, because we've designed this test, this is how we designed our hypothesis test. If we got 72 brown-eyed people, then we would keep the notion that 80% of people in the town have brown eyes, because it's close to 80, because it's close enough to 80 in our test. So 72, 71, 73, 74, 75, up to 89 is our acceptance region. But any numbers, any potential numbers outside of that would be in our critical region, because those numbers would lead us to reject H0. So some of you guys may be wondering, why are we not including decimal numbers in this? Because remember, okay, you can't have a decimal number of people with brown eyes, okay? this is discrete data. Discrete data has discrete potential outcomes. So it has a fixed number of potential outcomes. So 0 brown-eyed people, 1 brown-eyed person, 2 brown-eyed people, 3 brown-eyed people, all the way up to 100. Okay, can't have 1.5 brown-eyed people. Okay, so this is discrete data. So our critical region is a discrete set of numbers, and our acceptance region is a discrete set of numbers. Okay, so some more technical language as well that we need to bear in mind. So in our example, remember we had 2 regions. We had the critical region and we had the acceptance region. But we can actually break these regions into 3 sets. So we've got the lower tail critical region, what we call the lower tail critical region. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 70. So all these numbers here, 0, 1, 2, 3, 4, 5, all the way up to 70, are in the critical region. But the critical region has 2 parts. So it's got the lower tail critical region and it's got the upper tail critical region. So the lower tail critical region is the smallest numbers in our critical region. So 0 up to 70, these are the smallest numbers in our critical region. But the big numbers in our critical region, 91, 92, 93, up to 100, this is the upper tail critical region. And the numbers in between are the acceptance numbers, the numbers in the acceptance region. So the acceptance region splits our critical region into 2. The lower tail critical region, so the lower tail of our distribution of numbers, and the upper tail of our critical region, the upper tail of our distribution of numbers. Now, again, a couple more technical terms. So, one more technical term, really. We call the critical value. So the biggest number in our lower tail critical region, which here is 70, we can see that's 70. We call that the critical value, okay? So the critical value is the biggest number in our lower tail critical region, such that we reject H0. So it's the biggest number in our lower tail critical region. But in a 2-tail test, because remember, this is a 2-tail test, we got 2 tails of the distribution, the lower tail and the upper tail critical regions. The smallest number in our upper tail critical region is also a critical value as well, so 91. Okay, so 91 is also critical value. So in this hypothesis test, we have 2 critical values. Okay, so 70 and 91. Now, as I was trying to allude to, 2-tail tests normally have 2 critical regions, so a lower tail critical region and an upper tail critical region, and so therefore they have 2 critical values. Now, that's not always the case. It may not always be true that, okay? In our test, we could have just ignored this upper tail critical region. We could have just said, okay, so 71, 72, all the way up to 100, that's in our acceptance region. We could have decided that, okay? We could have decided that. There's nothing stopping us from deciding that. But in this hypothesis test, we decided to have 2 tails to the critical region. So the lower tail critical region and the upper tail critical region. So the 2-tail test, it's very likely that you'll have 2 critical regions, your lower tail and your upper tail critical region. Doesn't have to be true, but you know, it's likely that to be the case, and most certainly it probably will be the case in exam questions. But for a 1-tail test, you will only have 1 critical region. So for a 1-tail test, it's impossible to have 2 critical regions, right? So 2 parts of the critical region. If you're looking at a 1-tail test where you've got so I mean, if we remember what I was saying on the slide, let me actually go back to the slide we had before. Actually, no, it won't let me do that. So remember, we could have a null hypothesis, which would have said the proportion of people with brown eyes in the town is less than 80%. So we would call that a lower tail test, a 1-tailed lower tail test, because we're investigating whether the proportion is less than, with a less than sign. Okay, so that we're looking at the lower tail, less than lower tail of the distribution. Okay, so with these 1-tail tests, we only have 1 critical region. So either a lower tail critical region, if we're doing a lower tail test, or an upper tail critical region with an upper tail test. And so therefore, with a 1-tailed hypothesis test, you will only have 1 critical region, 1 critical value, because you have 1 critical region. With a two-tailed test, you could have, and it's more likely than not, you could have two critical regions, a lower tail critical region and an upper tail critical region, and so therefore you have two critical values. Again, hopefully this makes sense. Any questions, please do drop them in the comments. So again, we're going to move on to another technical term, the significance level of a hypothesis test. So a definition that you need to learn is that the significance level, the significance level of a hypothesis test is the probability that you reject the null hypothesis under the assumption that the null hypothesis is true. Okay, so remember, we've got these two hypotheses, H0 and H1. In our case, H0 is the probability of brown-eyed people being 80%. H1, the alternative belief, your new belief, is the probability of brown-eyed people in the town is not 80%. So the probability that you reject the idea of people in your town having brown eyes not being 80%, the probability that you reject the null hypothesis, assuming it's true, is called the significance level of the test. Sometimes it's called a type 1 error. Okay, so especially if you do maths at university or stats at university, or maybe economics, you may see this term type 1 error. So that's exactly the same as the significance level. So significance level, type 1 error, they mean the same thing. But in A-level maths, you don't really see this term type 1 error, you just see significance level. So going back to the example, okay, so remember, we're going to take 100 people, a sample of 100 people in our town, and we're going to determine if they have brown eyes. So we define, so let's think about this. So we want to get, so we're going to count the number of brown-eyed people. So we'll define, quote, success to be identifying someone with brown eyes. Okay, so a successful result would be someone has brown eyes. So we're going to ask every one of these 100 people, do you have brown eyes? Success, we're going to call, yes, you got brown eyes. Failure, we're going to call that not having brown eyes. So if someone says, no, I don't have brown eyes, or if we see that someone doesn't have brown eyes, we would define that to be a failure. So imagine like you've got like a tally chart, success, failure, right? So when we get someone with brown eyes, we're going to put that, we're going to put a tally, a tally mark under success. And if we get someone with not brown eyes, then that would be identified as a failure. That's what we're going to do in this test. So if we assume that H0 is true, okay, so this belief that 80% of people in the town have brown eyes, if we assume that's true, then that means the probability of randomly selecting a person in the town with brown eyes is 0.8. Okay, so again, just assuming that we have 80% of people in the town with brown eyes, then it means the probability of selecting someone with brown eyes is 80%, so 0.8. So again, what are we going to do in our investigation? Just to be really clear, we're going to count the number of people in the town who have brown eyes out of 100 people. And this is a key thing as well. So each of these 100 people in the sample can be thought of as a trial. So we can think about this in this investigation where we're going to ask every one of these 100 people, do you have brown eyes? We can think about every member as a trial, okay? So we're going to go up to person number 1 and ask them, do you have brown eyes? Yes or no? That's trial number 1. Then we're going to do our second trial. Ask person number 2, do you have brown eyes? Yes or no? Move on to trial number 3. Person number 3, do you have brown eyes? Yes or no? So each one of these 100 people in our sample, so our sample size, can be thought of as a trial. And going back to why we take a random sample in A-level maths, we take a random, so the sample we take is random. So that means that every sample member's eye color is independent from each other. Okay, so in an ideal world, that's what we want. We don't want, to take people from the same family where, if you come from the same family, your eye color is probably going to depend, the eye color of your parents has an impact on the eye color of the child, right? So there's dependency on the outcome. In this case, we're going to assume that we take a random sample. So every sample member's eye color is independent from each other. Does this ring a bell? Hopefully it does. Do you remember the binomial distributions? Do you remember the binomial distribution is about counting the number of successes you have out of a fixed number of trials. Okay, that's what a binomial distribution is all about. So the number of brown-eyed people in our sample of 100 is a random variable. Okay, so it's random. So why is that a random variable? So it's a random variable because if you took infinitely many samples, so you got this town with, let's say, 50,000 people. If you run a computer program which took infinitely many samples of 100 out of your 50,000 people, the number of brown-eyed people in each one of those samples is going to be different, isn't it? Because there's, because there's a proportion of brown people in your town. Sorry, there's a proportion of brown-eyed people in your town. So therefore, it's a random variable, right? Your samples will all have different numbers of brown-eyed people. So the number of brown-eyed people in your sample of 100 is a binomial random variable. It follows a binomial distribution. And why is this the case? Because we have a fixed number of trials, and that's key, and that's the key element of a binomial distribution. You've got to have a fixed number of trials. So in our case, 100, a sample size of 100. We have a fixed probability of success. So again, if we assume our null hypothesis, 80% of people have brown eyes in the town. So that's a success probability of 0.8. The trials are independent from each other because our sample is random. We took a random sample, so that means the trials are independent. So the the outcome that one person has brown eyes doesn't affect the fact that someone else may have brown eyes or not. Okay, because we've got a random sample. So if we call capital X the number of brown-eyed people in our sample, and again, the number of brown-eyed people in our sample will be random because, again, it depends on who is in our sample in the first place. Because, depending on who's in the sample, the number of brown-eyed people in the sample is going to be different. It's a random variable. Then this X, this number of people in our sample with brown eyes, is a binomial distribution with 100 trials and a p-value, a probability of success, is 0.8. Okay, so this is just going over binomial distribution again. So again, X, the number of brown-eyed people in the town, the number of brown-eyed people in our sample, of 100 is a binomial distribution. Okay, so now this is why I said at the start of the video, please do make sure you know how to use the binomial distribution before you watch this, because we need to do this now. So now that we've identified that in our sample of 100 people, the number of people that we get with brown eyes is a binomial random variable, so it follows a binomial distribution. Now we can calculate probabilities. So now we can calculate the probability of rejecting H0. Now we can calculate the significance level. So remember, the significance level is the probability that we reject H0, assuming that H0 is true. So assuming that the probability is 80% in our investigation here. So assuming that the probability of brown-eyed people in our town is 80%, what is the chance that we would reject H0? So what is the chance that we pick a number of people in our sample with brown eyes between 0 and 70 and 91 and 100? So remember, the critical region is the set of numbers that would lead us to reject H0. So 0 brown-eyed people, 1 brown-eyed person, 2 brown-eyed people, all the way up to 70 in our lower tail critical region, and then in our upper tail critical region, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. So the critical region, remember, our critical region is composed of our lower tail critical region and our upper tail critical region. So in our investigation that we're doing, we decided this in this specific investigation, and we decided this was our critical region. So the question is, if you want to work out the significance level, aka the probability that you reject H0, then we need to work out the probability that we get 0 successes, or 1 success, or 2 successes, or 3 successes, or 4 successes, or 5, or 6, or 7, up to 69, 70, or 91, or 92, or 93, 94, 95, 96, 97, 98, or 99, or 100. We need to work out the probability that out of our sample of 100 people, we get any number of these successes, and then add those probabilities up, because that will tell us the probability that we reject H0. So remember, 100 people in our sample, we will reject H0 if 0 of those people have brown eyes, or if 1 of those people have brown eyes, or if 2 of those people have brown eyes, or 3 or 4, up to 70. So our lower tail. And then we go up to our upper tail. So if 91 people have brown eyes out of 100, we reject H0 again. Or if 92, or if 93, 94, 95, up to 100, again, we reject H0. So to work out the probability that we reject H0, so to work out our significance level, aka the probability that we reject H0, we need to add up these probabilities. The probability that 0 people have brown eyes, 1, 2, 3, 69, 70, 91, 92, 99, up to 100. Yeah, that's what we need to do. So again, if X is the number of brown-eyed people in our sample of 100 people, then the significance level is the probability that 0 people have brown eyes, plus the probability that 1 person has brown eyes, plus the probability that 2 people have brown eyes, plus the probability that 3 do, 4 do, 5 do, up to 69, plus 70. And then remember, we forget 71, 72, 73, up to 89. We forget those because that's not in our critical region. That's our acceptance region. We want to find the probability of rejecting it. We want to find the rejection probability. So we take numbers in our critical region. So we don't do 71, 72, 73, 89, 90, but we do 91, we do 92, 93, 94, 95, 96, 97, 98, 99, 100. We're going to add up all these probabilities together, and that's going to be our significance level. That's our probability of rejecting H0. Now, obviously, that's a lot of calculations to do, but we can simplify the calculations, okay? So remember, right, we've got, again, the lower tail critical region, so 0, 1, 2, 3, 4, 5, 6, 7, up to 70. We've got the upper tail critical region, so I've used red brackets here just to make it really clear. Lower tail critical values, upper tail critical region values, and we're going to add those together. So the first key point is that in my first pair of red square brackets here, the probability getting 0 successes, 1 success, 2 successes, 3 successes, up to 70, this is equal to the probability that you get less than or equal to 70 successes. Okay, so you could get no successes, 1 successes, 2 successes, all the way up to 70. So that if you add up all 71 of those probabilities, and it's 71 probabilities because we got the probability getting 0 success as well. So we got 71 different calculations. But remember, if we add those all up, this is exactly the same as the probability of getting less than or equal to 70 successes. Okay. So the probability of rejecting H0 in the lower tail of the distribution is the probability that X is less than or equal to 70. Okay. Now let's go to the upper tail of the distribution. So remember, we're going to look at our second part of the calculation for the significance level. So 91 successes, 92, 93, 94, up to 99, 100. So the probability of 91 successes plus 92 successes plus 93, all the way up to 100 successes, is the probability that X is bigger than or equal to 91. Okay, so again, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100 successes. That is bigger than or equal to 91 successes. Okay, that's what that is. And remember, we don't go any further than 100 because we've got a sample of 100. Okay, and our binomial distribution has n equals 100, so the number of trials is 100. Okay, so we don't need to worry about. So this X is bigger than 91. Sorry, bigger than or equal to 91 doesn't include 101, 102. Doesn't include that because the maximum value is 100 anyway, because we specify that with our binomial distribution. So bear this in mind as well, okay? So remember that the probability that X is bigger than or equal to 91 is exactly equal to the probability, is exactly equal to 1 take away the probability that X is less than or equal to 90. So why is this? Let me try and go through this just to be really clear about why this is the case. So let's say you've got like a number line like this. So you've got, so I'm going to put 88 there. Sorry, that should be an 8 there. Let me try and make that a little neater. 88 there, 89 there, 90 there, 91 there, 92 there. And then obviously, we can go on 93, 94, so on and so on. So the probability that we get 91 or more successes would be adding up this probability, this probability, this probability. So all these probabilities bigger than 91. Okay, all those probabilities there. But this is exactly the same. So remember, probabilities add up to 1. Okay, so the probability of 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 100, all adds up to 1 because probabilities add up to 1. So if we do 1 take away all of these probabilities, so the number of successes being less than or equal to 90, then we're just left with 91 successes, 92, 93, 94, 95, 96, 97, 98, 99, 100. So the probability that you get 91 or more successes is the same as 1 take away the probability that you get less than or equal to 90 successes, because of the fact that probabilities add up to 1. So hopefully that made sense. But if you've done binomial distribution, I'm sure that will make sense. So just a little reminder. Okay. So let's go back to the presentation. So again, 1 minus the probability that you get 90 or less successes is the probability of rejecting H0 in the upper tail of the distribution. So that the total significance level is the probability that you get less than or equal to 70 successes, plus the probability that you get more than or equal to 91 successes. And because of this calculation that we did over here, okay, this calculation here that we just explained, this is exactly the same. So exactly the same as the probability of getting less than or equal to 70 successes, plus the probability of getting less than or plus the number 1, take away the probability of getting less than or equal to 90 successes, because the probability, the probability of getting more than or equal to 91 successes is the same as the probability of getting less than or equal to 90 successes taken away from the number 1. Okay, so this calculation we just did back there. Okay, so again, hopefully that does make sense. Right, so let's go to the next slide. Okay, so calculating the significance level with a calculator. So obviously, you know, this is gonna, if you want to do this by hand, you could do this by hand using the binomial distribution formula for probabilities, but it's going to take you a very long time because, I mean, if we go back, sorry, let me see if I can make my presentation go back. There we go. So yeah, as we said back here, I mean, we're adding up 71 probabilities here, plus the number 1, and then take away 91 probabilities there. We're going to be here for a very long time if you use our binomial distribution formula. So the good news is we can use the calculator to do these calculations. So the significance level, as you just said, you know, we just said this. So the significance level, the probability that we reject H0 for our designed hypothesis test is the probability that you get less than or equal to 70 successes, plus 1 take away the probability you get 90 or less successes. Now, let's try and calculate the probability that you get less than or equal to 70 successes using your calculator. So you're going to go to the statistics menu. So, I mean, to be honest with you, it depends on your calculator make, but I have the FX, the Casio FX 9750. I think most of you guys, if you do Edexcel and AQA, you'll probably have the FX 911. I think it's 911G or 911E, I think. I can't remember, to be honest with you. But in that case, I think it's the same. So you want to go to your statistics menu in your main menu. So go to main menu, statistics. You want to press the distribution button. So on my calculator, the FX 9750, you press F5 to go to distribution. And then you want to press the binomial option. So again, on my calculator, it's F5. And then you want to go to BCD, so binomial cumulative distribution. You want to press that. So why do you want to press that instead of BPD, binomial PD? Why do you want to press binomial CD? Because binomial cumulative distribution accumulates binomial probabilities. It adds up binomial probabilities. So when you want to work out these probabilities where you've got inequalities involved, so the probability of getting less than or equal to 70 successes, remember, this is the same as the probability. This probability here is the same as probability you get 0 successes, plus 1 success, plus 2 successes, plus 3 successes. So you're accumulating probabilities. So when you're dealing with probabilities with these inequality signs, You want to use the BCD function, the cumulative distribution function, because you're accumulating lots and lots of binomial probabilities. So that's why you're using BCD. So then what you want to do now to work out this probability is you want to press x equals 70. So put 70 in the x part, because the maximum number of successes for this probability is 70. So this x value in your calculator, the little x value of your calculator, is the maximum number of successes. So that's how your calculator works. So the x value, remember, when you go to binomial CD in your calculator, x is the maximum number of successes. In this case, it's 70. So we put in 70, we put number of trials 100, we put a p-value in of 0.8, because we are assuming H0, so we're assuming that the proportion of brown-eyed people in the town is 80%. We're assuming that, so that's 80% of 0.8. Now, when you do that, you'll get an answer of 0.01125. So the probability that you reject H0 in the lower tail of your distribution for the lower tail critical region is about 1%. So 0.01125, so 1.125%. Now let's calculate. So remember, we got to calculate the significance level, which is this probability we just got, plus 1 take away this one. So why are we doing 1 take away this probability? Why aren't we just doing the probability of x being bigger than or equal to 91? So remember, if we go back here, so remember the probability that you reject H0 on the upper tail of your data is the probability that x is bigger than or equal to 91. So why can't we just use the calculator to work out this probability straight away? So remember, your BCD function, your binomial CD function, is programmed such that the x value you put in is the maximum value, right? But we want the probability of getting more than 91 successes. So that's why we've got to do this 1 minus calculation, because then we can do 1 minus the probability of 90 or less successes. So then we can put 90 as our x value in our BCD function in the calculator. Okay, so we just did this calculation here. So to calculate the probability that we get 90 or less successes, again, same thing, distribution, binomial CD. Now our x value becomes 90. So remember, that x value in your BCD function is the maximum possible number of successes, okay? And if you do that, you get an answer of 0.9977, okay? So 99.77%. So the significance level for this test is 0.01125 plus 1 take away 0.9977 using this formula up here we got, okay? So actually what we can tell here is that the probability that you get more than or equal to 91 successes is the number 1 take away 0.9977, which is 0.0023, okay? But the reason why we've got to do this 1 minus calculation that we just did here is because of how your calculator is programmed. Unfortunately, your calculator, again, if we go back to this slide here, unfortunately, there's no way that your calculator can work out this probability, this probability x being bigger than or equal to 91 straight away. So you have to do this this thinking calculation where you say, okay, the probability you get more than or equal to 91 successes is 1 take away the probability that you get less than or equal to 90 successes, which you can now put this probability in your calculator because your x value becomes 90 in the BCD function in the calculator. So the significance level for this hypothesis test is 1.355%. So the probability that you reject H0 for this hypothesis is 1.355% for our tailor-made designed hypothesis test. So again, let's think about our conclusions. So we had a sample of 100 people, and we originally assumed our H0. We assumed that the proportion of people in the town with brown eyes is 80%. If we assume that to be the case, and we do our binomial distribution calculator, we found out that there is a 1.355% chance that out of our 100 people, we reject H0. So out of our 100 people, there is a 1.355% chance that either 0, 1, 2, 3, 4, 5, 6, all the way up to 69, 70, or 90, 91, 90, 99, 100 people have brown eyes. Actually, I think have I made an error with this? Yes, sorry, I have. Sorry, yeah, I've made an error of this here. Ignore this here. 90 is not included in this. Sorry, it's just 91, 92. 90 is not involved. Sorry, this is a mistake there. Okay, so again, we have a 1.355% chance of rejecting H0. So we have a 1.355% chance of getting 0 successes, 1 success, 2 successes, up to 69, 70, or 91, 92, 99, 100. We have a 1.355% significance level, a 1.355% chance of rejecting H0. Forget this 90, this was a typo. This is an error there, sorry. Okay, right. So then now, again, so in our tailor-made hypothesis that we designed, there was a 1.355% chance we reject H0. So let's just, again, think about this in context. So let's say that we've got a sample of 100 people, and let's say 65 of those people had brown eyes. Then if that was to be the case in your sample, we would reject H0, okay? Because 65 is in our critical region, okay? It's in our critical region of values. So 65, anything between 1 and 70 is in the critical region. 65 is in the critical region. So we reject H0. So we reject the notion that the proportion of brown-eyed people in the town is 80%, because we've got a number far away from the number we thought because it's in our critical region. So, sorry, let me just run about this here. Okay, so we tailor-made this hypothesis test. We come up with a random hypothesis test, which again, as I said, is fine. Again, you know, as a statistician, you're welcome to do any hypothesis test you like. You're welcome to design a critical region. That's fine. You can do that. But was this a good hypothesis test? So there was this hypothesis test we just did here, a quote good hypothesis test. So let's have a think about whether it would be. Now, the key thing is with these hypothesis tests is that we want our significance levels to be small. So we want the probability of rejecting H0 to be small. Now, why do we want that? So normally around 1% to 5% is what it would be a good significance level. So as I just said, why do we want our significance levels to be small? So we don't want to disregard our existing belief, our H0, our null hypothesis, unless we have strong evidence to suggest that we need to disregard it. So a good example would be medicines, right? So let's say, right, that you've come up, you've gone to the lab and you've got this new medicine, right? This brand new medicine which is supposed to cure, which people think will cure every disease possible. Okay, so you've got this new superpowered special medicine, right? And you want to trial this medicine on patients. You want to do, you know, a trial, and you want to see, does this new medicine cure people of their diseases? Okay, so that's what you want to do. You want to test, does this medicine cure people of diseases? So your H0, your the status quo hypothesis, the existing theory, when you go into this test, is you have to assume that the medicine doesn't have an effect. Okay, so when we go into these hypothesis tests, we have to assume that nothing has changed. We have to assume that this new thing that's been introduced doesn't have any effect. We have to assume that, you know, if we go back to the example we just had, we have to assume the proportion of brown-eyed people in the town is 80%. We have to assume what was the initial original assumption that everyone assumed. We've got to assume that the medicine has no effect. Okay. Then we're going to trial out this medicine on all these people, and we're going to investigate, we're going to collect data, and we're going to investigate whether it does have an effect. We need the probability of we need the probability of rejecting H0 to be low. We need we need our rejection region, our critical region, to be low, as low as, you know, we can have it, because we need to be absolutely certain this medicine really does cure disease, right? It really does cure every disease. So we can't just, you know, if we've got a really high significance level, like, you know, 20%, that means we got a 20% chance that once we do our investigation and collect the data, there's a 20% chance that we turn around and say to everyone, this medicine cures every disease possible, right? But to be honest, that's not, you know, it's not a very good hypothesis test, because you can't go around saying that this medicine cures every disease possible unless, you know, the data really suggests that it does. So we want the probability of rejecting H naught, the probability of rejecting the idea that the medicine doesn't have an effect, to be low. We want that probability to be low because we don't want to go around making false claims that this medicine cures diseases, right? Similar thing with the hypothesis test in our presentation that we're looking at today about brown-eyed people. The initial statistic we had was that 80% of people in the town have brown eyes. We don't want to, you know, we don't want to make bold claims that that percentage is not true unless we really have strong evidence, unless the data really does suggest that that would be a silly probability. 80% would be a silly probability. Okay, so your significance level is quite low. We choose a low significance level. We want to make sure the significance level is low because we don't want to easily reject H naught. We don't want to easily reject our status quo belief, because if we are going to reject the belief, if we are going to reject, for example, the medicine example, if we're going to turn around and say to everyone, yeah, this medicine cures every disease possible, we've got to be absolutely sure about that. So we've got to, our data has got to be so unlikely that actually we have to turn around and say, yeah, the data we got was so unlikely, assuming H naught was true. The data, you know, if we take our sample of 100 people and it cures all 100 people, well, that's so unlikely. We have to turn around and say to everyone, yeah, we think it does cure disease. Do you get what I'm saying? Hopefully this is making sense, right? So we want that significance level to be low. But you're probably asking, why can't we just pick an absolutely minuscule, tiny significance level like 0.1%? Well, I mean, you could have a 0.1% test if your sample size is big enough. But why don't we go to like, you know, 0.0000001%? Why don't we have like, you know, 1 times 10 to the power of minus 50 as a significance level? Why don't we have an absolutely tiny, why don't we have 0% as a significance level? Because if the significance level was too small, we would never reject H naught in the first place. So, I mean, there's no point in doing a hypothesis test if it's impossible to reject H naught. Obviously. So, you know, we've got two hypotheses, H naught, H1, the null hypothesis versus the alternative hypothesis. If the significance level was 0, or if it was like 0.0000001%, that means there's virtually no chance that you reject H naught. Okay. What's the point of collecting data and doing a hypothesis test if there's no chance you're going to, if you there's absolutely no chance at all that you reject one of your hypotheses? You got two theories. You're going to collect data, and then your data is going to suggest whether you go with one theory or the other theory. That's what statisticians do. You collect your data. Does the data suggest one theory or does it suggest the other theory? What's the point in collecting data in the first place if it's impossible to get one of those theories to be true, right? If it's impossible to reject the null hypothesis, then that means that the null hypothesis is always true. So what's the point of doing a hypothesis test in the first place? What's the point of collecting your data in the first place? Okay, so the significance level should not be too small, but it needs to be small because, as we said here, we can't go around making bold claims, okay, unless the data we collected was pretty unlikely to get, if you get what I'm saying. Okay, hopefully that's, again, making sense. We want a small significance level. So to have a good hypothesis test, we want a small significance level. So about 1%, 2%, 3%, 4%, 5%. These are good numbers. So some more observations about our test about brown-eyed people. Okay, so remember, we did our calculation and we found the significance level was 1.355%. So this is pretty decent. I mean, we've got a 1.355% chance of rejecting H naught. It seems like a pretty good hypothesis test, you know. We again, the facts in the town that we had before we did the investigation was that 80% of people in the town have brown eyes. We have this suspicion it was something different, but a 1.35% chance of rejecting H naught is pretty decent because, again, it means our test is it's a strong test. It's a good test. It's not the chance of rejecting H naught is not too tiny, but it's not big. Okay, so it's a good test so far. It seems pretty decent. I was trying to find a word, but I can't. I can't think of the word that I was trying to find. It was on the tip of my tongue, but it's a word that I'm trying to find type of test, right? It's a good test, but I'm not trying to use the word good. I'm trying to find another word for it, but I can't find the word. Anyway, let's move on. Wasting time now. So again, the probability that we reject H naught by obtaining a number in the lower tail of the critical region was the probability of getting less than or equal to 70 successes, and we calculated that to be 1.125%. The probability that we rejected H naught by obtaining a number in the upper tail critical region was that probability there. So 1 minus the probability that we get less than or 90 successes, which, as we explained before, is the same as the probability that we get 91 or more successes. So that was one takeaway 0.9977, which was 0.23%. So what is this telling us? So it tells us that we're more likely to reject H naught by obtaining a number in the lower tail of the critical region compared with the upper tail critical region. Okay, so we got a 1.1% chance of rejecting H naught. So again, sample of 100 people. We've got a 1.1% chance of rejecting H naught by picking a number less than or equal to 70. So obtaining a number, sorry, not picking, because we're collecting data, we're recording data, we're obtaining data. We've got a 1.1% chance roughly of getting less than or equal to 70 successes. Okay, so we've got a 1.1% chance of rejecting H naught in the lower tail. But we've got a smaller probability, a 0.23% chance of rejecting H naught by obtaining a number in the upper tail critical region. So what is this telling us? So basically it's telling us that we're 5 times more likely to reject H naught in the lower tail critical region compared with the upper tail critical region. Because if you go to your calculator and do 1.125 divided by 0.23, it's about 4.8 times more likely to 5 times more likely. So what is this telling us, right? What is this, kind of telling us about how good our test is? The key thing is in an ideal world, we want the probability of rejecting H naught in the lower tail to be the same as the probability of rejecting H naught in the upper tail. We want a symmetrical hypothesis test. We want an even hypothesis test. Okay, so as I just said there, ideally we want the probability of rejecting H naught in the lower tail to be the same as the probability of rejecting H naught in the upper tail, because we want to make sure that the distribution is evenly spread out. So again, going back to our brown-eyed people example, if 80% of people in the town have brown eyes, then it means we would expect in our sample of 100 people, 80 of those to have brown eyes. Okay, so we want our significance level in both the lower tail and the upper tail to be the same. We want the probability of rejecting H naught in both tails to be about the same, because we want to try and have a symmetrical test, an even test, where the probabilities are balanced on both the lower tail of the hypothesis test and the upper tail of the distribution for the hypothesis test. So again, going back to our hypothesis test that we designed on the spot right now, we were 5 times more likely, again going back to the calculation back here, so we were about 5 times more likely to reject H naught in the lower tail compared with the upper tail. Again, in an ideal world, in a good hypothesis test, those probabilities need to be about the same. So to improve our hypothesis test, and this is what statisticians usually do rather than what we just did, was instead of choosing the critical region before we collect the data. So remember, what did we do in our test today? We chose the critical region. We chose the values that gave us a rejection. We decided before we did the test, okay, so if we get 0 up to 70 successes or 91 up to 100 successes, we reject H naught. We chose that. We chose the critical region. So what statisticians usually do, and what you will do in your exam questions, what you're very likely to do in your exam questions, is instead of choosing the critical region, you choose the significance level before the test. So you actually choose the probability of rejecting H naught before you do the test, going into the test, rather than the critical region. So 1%, 2%, 5%. So that's what we usually do before the test, rather than actually choosing the critical region ourselves. We choose the significance level instead. So in a two-tail test, like our test about brown-eyed people, what we do is we halve the significance level. So we devote half of the significance level to the lower tail, so the lower tail critical region, and half of the significance level to the upper tail critical region. So half and half. As we were just saying here, you know, in this bullet point up here, we want the probability of rejecting H naught on the lower tail to be the same as the probability of rejecting H naught on the upper tail. So we split our probability of rejecting H naught into two, the lower tail, the upper tail, into half. But in a one-tail test, so in our example about brown-eyed people, this was a one-tail test, but this was a two-tail test. But in a one-tail test where you're only investigating whether a probability or a proportion or a percentage has decreased or increased. So in a one-tail test, you were investigating a decrease or an increase, not a change. That's two tails. So in our example, again, we're investigating, is the proportion of brown-eyed people different from a change in 80%? That's two-tailed. This could be lower, could be higher. But in a one-tail test where you want to investigate, has it decreased or has it increased? Then you dedicate all of your significance level to the corresponding tail. So if you're doing a 1% test in the upper tail of the distribution, then all of your significance level is devoted to that upper tail of the distribution. So you don't have a lower tail critical region, you only have an upper tail critical region. One tail tests are easier than two tail tests, so that's kind of why I'm doing the two tail test example. But if you get the two tail test example, hopefully the one tail test example makes sense. That's why I'm doing the two tail test example in today's presentation. So how are we going to refine our hypothesis test? So we're going to have the same setup as before. Okay, we're going to take a sample size of 100 people. The probability of success is 0.8, so an 80% chance, assuming H naught, assuming that 80% of people in the town have brown eyes. Our probability of success of getting brown-eyed person is 80%, 0.8. So assuming H naught under the null hypothesis, the number of brown-eyed people in our sample is a binomial distribution, 100 as our sample size, so 100 trials, and a probability of success, fixed probability of success, is 0.8. So again, our null hypothesis, P is equal to 0.8. Alternative hypothesis, P is not equal to 0.8. Two-tailed test, remember, two-tailed, not equal to in our alternative hypothesis means a two-tailed test. An inequality symbol, less than sign or a greater than sign, means one-tailed test. Now, let's, instead of, again, like we did before, we pick the critical values, we pick the critical region. We're not going to do that now. We're going to refine our hypothesis test. We're going to pick the significance level. Let's pick a 1% significance level. So, because we're doing a two-tailed test, as I just said on the previous slide, we need to split the significance level into half. 0.5% chance of the lower tail, 0.5% chance of the upper tail. So 1 divided by 2 is a half. Split 0.5% chance of rejecting H naught to the lower side of the distribution, and split a 0.5% chance of rejecting H naught to the upper side of the distribution. So this makes the test a more even test, a better hypothesis test. So now, instead of, again, I'm kind of repeating myself here, but I just really want to make sure you guys understand this. So before, in the hypothesis test we randomly came up with before, we chose the critical region and then we calculated the significance. We calculated the significance level. This time we chose the significance level, so now we can calculate the critical region. So remember, this is a two-tailed test, so we have two parts to our critical region: the lower end and the upper end. So again, what we're going to do to calculate our critical region is we're going to use our calculator. We want to go again to our stat menu. We want to go to the distribution section, and we want to pick the binomial distribution and binomial CD. So again, we're accumulating probabilities. We're looking at different regions of our distribution. We want to go to binomial CD. So we're going to have n as 100, P is 0.8, because again, we're assuming H0, we're assuming our null hypothesis. And for X, we're going to plug in random numbers, okay? We're going to plug in random numbers. So for example, I plugged in 75. So when I did the presentation, I plugged in 75. So if you plug in 75, you get 0.1314. So let's just remember what this is telling us in our calculator. So this is telling us that the probability that X is less than or equal to 75 is 0.1314, so 13.14%. We want to try and get numbers as close to 0.5% as possible. Remember, the probability of rejecting H0 in this hypothesis test is 1%. That's our significance level, but we're splitting our significance level into two. 0.5% in the lower tail, 0.5% in the upper tail. Remember, the critical region is the set of values that we could obtain from our investigation that would lead us to reject H0. So these X values could be in our critical region. We want to try and get X values that give us a probability, a binomial CD probability close to 0.5. And then we can make some conclusions about our critical region. So, I mean, what we just got there was 13.14%. Now, that's not quite near 0.5, is it? So let's try some lower numbers. Okay, so remember, the probability that X is less than or equal to 75 is obviously going to be a bigger number than the probability of getting less than or 70 successes, because 75 successes, less than or equal to 75 successes include 71 successes, 72 successes, 73 successes, 74 successes, 75 successes. But if we go to 70 or less successes, so in our binomial CD, for X equals 70, again, and number of trial values is 100, P value 0.8, execute that, what do we get? So this time we get 0.01125, so 1.125%. So we're getting close to 0.5%. Let's try 69. So instead of our 70 as our X value, let's put 69 as our X value. And if we do that, we get 0.006059. So 0.6059%. So we're very, very close to 0.5% actually. Let's just go down one more to 68%. Sorry, 68 successes or less. So back to the binomial CD function. X is going to be 68, number of trials 100, P value 0.8. And if you do that, you'll get 0.00313. We're now going to stop. And we're going to stop there because we've got two values here, two probabilities, one bigger than 0.5% and one smaller. So these two probabilities, these consecutive number of successes, 69 and 68, they're next to each other. And we've got a probability bigger than 0.5% and one less than 0.5%. So now we need to stop and have a little think. So now we can identify the lower tail critical region. So I'm just writing out the probability we just got there. So with 69 or less successes, we had a 0.6% chance doing that. And that's bigger than 0.5%. That tells us that 69 is not in our critical region because it's too close to 80. Okay, so the probability that we get less than or equal to 69 successes from our investigation about brown eyes is bigger than the 0.5% significance level, so bigger than the 0.5% chance to reject the H0 in the lower tail. So it's bigger than, it's a more likely chance than 0.5%. So we're more likely to get 69 or less successes than 0.5%. So 69 is not in our critical region. So it's just not in our critical region because basically it's too close to 80. So remember, okay, we're assuming that the probability of getting a brown-eyed person is 80%. If you've got a sample of 100 people, how many brown-eyed people would you expect? You expect 80 because 80% of 100 is 80. So 69 is not in our critical region. It's a little bit too close to 80. But when we go to 68, the probability that we get 68 or less successes is 0.313%. 0.313% is less than 0.5%, our lower tail critical region probability of rejecting H0. So 68 is in our critical region because now 68 is too far away from 80. So again, we expect to get 80 successes out of 100. because we assume the probability of success to be 80%. But 68 is in our critical region because the probability of getting 68 or less successes is 0.313, which is less than 0.5%, which is the 0.5% probability that we dedicated to the lower tail of the distribution. So the probability of rejecting H0 in the lower tail. So that means that obviously 67, 66, 65 will also be in our critical region as well, because obviously the probability of getting 67 or less successes, or 66 and less successes, or 65 and less successes will be less than 0.313, so even smaller. So all these numbers will be in our critical region. So our lower tail critical region will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 66, 67, 68. So let's just think about this. We've got our sample of 100 people. We're going to ask them, do you have brown eyes or not? If 0 people have brown eyes, we reject H0. If 1 person had brown eyes, we reject H0. If 2 people have brown eyes, reject H0. All the way up to 66, 67, 68, we reject H0. But if 69 people had brown eyes in our sample, then we would actually accept H0. We would retain H0. We would not reject it because it's not in the critical region. So that's our lower tail critical region. As I was saying before, in 2-tail tests, you normally have two parts of the critical region: the lower tail critical region, the upper tail. In a 1-tail test, you don't have 2 critical regions. You only have 1 critical region. So if you're doing a lower tail 1-tail test, you only have the lower tail critical region. If you're doing an upper tail 1-tail test, you only have the upper tail critical region. Because this test is a 2-tail test, we need to see if there is an upper tail critical region. So there may not be. With a 2-tail test, we may not necessarily have 2 parts of the critical region, but normally we do. And in definitely most exam questions, most hypothesis tests, we will. So identifying the upper tail critical region. Remember that we devoted 0.5% of a significance level to the lower tail, 0.5% significance level to the upper tail. This time, instead of worrying about the probability of getting less than or equal to a certain number of successes, the sign of the inequality now changes. We're now interested in getting more than or equal to a certain number of successes. Why is that? Because again, this time we're looking at the upper tail of the distribution. Okay, we're looking at numbers bigger than, so the average, again, with this brown-eyed people hypothesis test, we expect 80 successes, but if we're looking at the upper tail of the distribution, so potentially 100 successes, 99 successes, we want the probability of getting more than or equal to these numbers, okay? So again, we're going to go back to the binomial CD menu in our calculator and follow the same procedure that we did as before. So n needs to be 100, p needs to be 0.8, and x are going to be random numbers that we decide. But this is the key thing. So remember, your calculator is programmed to use the less than or equal to symbol, not the bigger than or equal to symbol. That's how your calculator accumulates probabilities. So, for example, if we wanted to find the probability that we get bigger than or equal to 50 successes, this is the same as 1 minus the probability that we get less than or equal to 49 successes, as we explained before with the kind of number line explanation. So what I'm going to do is I'm going to pick x equals 88. Okay, so I'm going to go to my calculator, binomial CD, make sure you're in the binomial CD menu, and we're going to pick x equals 88. Okay, so pick x equals 88. So if we do that, x equals 88, number of trials 100, p equals 0.8, we get 0.9874, so 98.74%. So the probability we get 88 or less successes is 98.74%. But we want to find the upper tail critical region, so big numbers. So the the numbers in the critical region in the upper tail of our binomial distribution. So to find the probability that we get more than or equal to 89 successes, we've got to do 1 take away this probability. So 1 take away the probability of getting less than or equal to 88 successes. So 100% take away 98.74%, and we get 1.26%. So the probability that we get more than or equal to 89 successes out of our sample of 100. So the probability we get 89 or more brown-eyed people in our sample of 100 people is 1.26%. So a little bit bigger than 0.5%, but not too far away. So let's keep going. So the probability, so again, if we go back to the calculator and we put in binomial CD, so we're still in that CD option, that CD function, we're going to put x equals 89. Okay, so put that in the calculator. Number of trials still 100. We still got a sample size 100. P 0.8. What do we get? So we get 0.9943. So a 99.43% chance of getting 89 or less successes. So to calculate the probability that we get 90 or more successes, that's going to be one, take away the probability that we get less than or equal to 89 successes. Because again, remember our number line explanation, right? The chance you get more than 90 successes at something is the same as 1, because probabilities add up to 1. 1 take away the probability that you get 89 or less successes. So 100% take away 99.43%, which is 0.57%. Okay, so we're really, really close to 0.5% now. This is 0.5% significance level that we've devoted to the upper end of the distribution. But we're not quite below 0.5% just yet. So now let's look at the probability of getting less than or 90 successes. So again, binomial CD, your x is going to be 90. Put 90 as your x value in your calculator. Number of trials 100. P-value 0.8. What do you get? So you should get 0.9977. So 99.77%. So the probability that you get more than or equal to 91 successes is the number 1, take away the probability that you get less than or equal to 90 successes, which we just worked out on the calculator, which is 100% take away 99.77%, which is 0.23%. Now we're below, so the next consecutive number we've gone to 91 successes or more. This gives us a probability less than 0.5%. So now we need to stop and have a little think. Okay. So the probability that we got more than or equal to 90 successes was 0.57%. So this is bigger than 0.5%. So it's more likely than 0.5%, that 0.5% significance level that we decided. So that means that 90, the value 90 is not in our critical region. So it's too close to 80. It's a little bit too close to 80. So 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90 successes in our sample of 100. If we've got any one of those number of successes, it's too close to 80. So 90 is not in the critical region because the probability that we get 90 or more successes is bigger than the 0.5% chance of rejecting H0 at the upper side of the distribution that we decided before the investigation. It's a little bit too big. But if we go to 91 or more successes, we have a 0.23% chance of getting 91 or more brown-eyed people in our sample of 100. Now, 0.23% is smaller than 0.5%. So it's smaller than that probability of rejecting H0 on the upper side that we decided before the test. So therefore, 91 is in our critical region because it's a little bit too far away from 80. Again, null hypothesis, 80% of people in our town have brown eyes. So in a sample of 100 people, you expect 80 brown-eyed people. That's what you would expect, okay? Now, 90 people, if we got 90 people in our sample of 100 with brown eyes, it's a little bit too close to 80 because the probability that we get 90 or more people with brown eyes is 0.57%, which is bigger than 0.5%. But 91 people with brown eyes in our sample of 100 would mean that 91 is a little bit too far away from 80 because the probability of getting 91 or more brown-eyed people is 0.23%. So now we would reject H0 if we had 91 people with brown eyes in the sample. And obviously it's the same in 92, 93, 94, 95, 96, 97, 98, 99, 100. Okay, exactly the same because those probabilities are going to be even smaller than 0.23%. So the upper tail critical region is 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. So our critical region is 0 up to 68 and also 91 up to 100. And the acceptance region of our test is the numbers between 68 and 91. So 69, 70, up to 90. Okay. So again, we've got a sample of 100 people. If we found out in our sample that 69 people had brown eyes, then we retain H0. So we retain the notion that 80% of people in our town have brown eyes. We don't reject that. We've got to keep that. But if we collected our data and 68 people had brown eyes out of our sample of 100, then now we reject H0. Now there is evidence, enough evidence, sufficient evidence, significant evidence to suggest that the proportion of people in our town with brown eyes is not 80%. So a little bit more further calculation. So this is basically the conclusion for our critical region that we can decipher from our significance level. But let's do a little bit more analysis on that significance level. So before the test that we just did with where we chose the significance level, we specify that to be a 1% significance level. So we decided before the test arbitrarily that we have a 1% probability of rejecting H0. We decided that. But was the actual genuine significance level 1% for this test? So we decided before the test that we're going to have a 1% probability of rejecting H0. But given that we had a critical region of this, given that this was our critical region, is the probability of rejecting H0 actually exactly 1%, or is it something different? So remember, we have our lower tail critical region and our upper tail critical region. So our lower tail critical region was 0 up to 68, and our upper tail critical region was 91 up to 100, as we just worked out. The probability of rejecting H0 in the lower tail is the probability that you get less than or equal to 68 successes. And we worked that out because we did that on the calculator. We found out that was 0.313%. Okay, so the probability that you reject H0 on the lower side of the distribution is 0.313%. The probability that you reject H0 in the upper tail of the distribution is the probability that we got 91 or more brown-eyed people, which is 0.23%. So the actual probability that you reject the null hypothesis is the probability that you reject the null hypothesis in the lower tail, plus the probability that you reject the null hypothesis in the upper tail, which in this case is 0.23 plus 0.313%, which is 0.543%. So the actual significance level in this test is 0.543%, not 1%. So this is the thing with discrete distributions. So remember, a binomial distribution models discrete data. So when we've got distributions modeling discrete data, the reality is that the significance level we choose going into the test, which in this case was 1%, is not always going to be equal to the exact precise significance level, so the exact probability of rejecting H0, because the reality is that with discrete distributions, the probability of obtaining a certain outcome and adding up that probability with the probability of obtaining another outcome is not going to precisely add up to 1%. Okay, so these probabilities, these binomial probabilities of rejecting H0, they are not going to add up precisely to 1%. Okay, just because the likelihood of that is virtually zero with a discrete distribution. So yes, okay, we decided before the test we're going to do a 1% significance level test, and when you do an exam question, they will say to you, have a significance level 1% or 5% or 10%, whatever it may be, right? They will give you that significance level, and as a statistician you will choose that significance level, but it doesn't mean it's the actual probability of rejecting H0. So that's the significance level that you arbitrarily chose, but it doesn't mean it's the mathematical actual significance level. So you'll get sometimes exam questions which say to you, calculate the actual significance level, so the actual probability of rejecting H0. But with continuous, so when you do hypothesis testing with continuous distributions in year 13, you learn about hypothesis testing for normal distributions, in which case the significance level you choose will be actually bang on to the significance level of the of the actual test, the actual significance level. But with the discrete distribution, it's not always the case, and virtually all the time it will never be the case with these binomial distributions. So we've looked at all the theory, that we need for binomial distribution hypothesis testing. So as I said at the start of the video, this was going to be a long video, and hopefully that this is giving you a step-by-step guide to the theory behind binomial hypothesis testing. I am going to do a video on normal distribution hypothesis testing soon, but this was kind of like aimed towards year 12 students, this video. So hopefully that's given you some guidance and all the theory you need for binomial hypothesis testing. But again, any questions, leave them in the comments. But now, in the last kind of, few minutes of the video, let's look at how we would structure an exam answer. So let's say in an exam or in a test, you get this question. It is assumed that the proportion of brown-eyed people in the town is 80%. Sorry, in the town is 80%. So in our imaginary town that we had in our presentation. So John has a suspicion that the proportion is different from 80%. Okay, so key word here is different, okay? Different. Let's kind of underline this. This is really key. So with these statistics hypothesis test questions, we've really got to interpret the wording of the question. If there was a question, if it said John has a suspicion that the proportion of people with brown eyes is less than 80%, it becomes a one-tailed, lower-tail hypothesis test. If in the question it said John has a suspicion that the proportion of brown-eyed people is bigger than 80%, this becomes a one-tail test, but an upper-tail one-tail test. Because in this question here, it says John has a suspicion that the proportion is different from 80%, so it could be lower, could be higher. There are two possible options, so this is a two-tail test. So let's be really clear about this. So when you get these hypothesis test exam questions, you want to really read the question, interpret the words in the question, interpret the wording of the question. This is a two-tailed hypothesis test. This is going to take a sample of 100 people, just like we did in our two examples, 100 people, and he finds out that 67 people out of those 100 people have brown eyes. We want to do a test at the 1% significance level to test John's claim. Sorry, I shouldn't have the S there again. That should just be just a singular, not a plural. So we want to test John's claim that the proportion of brown-eyed people in the town is different from 80%. Okay, so how would we structure the exam, an exam answer to this? I mean, we've done the hard work already because we actually worked out the critical region for this test. But how would we do this properly? So I'm just going to rub out this here. So this would be how I would structure an exam solution. Sorry, let me just go back. So let P be the proportion of brown-eyed people in the town. Our null hypothesis is P equals 0.8. So the probability of picking a brown-eyed person is 0.8. Our null hypothesis is the probability is the probability not being equal to 0.8, because John had a suspicion that the proportion is not 80%. So this is a two-tailed test. Again, we want to be careful with the wording of the question because it could be a one-tailed test, but in this case, it's a two-tailed test. Let X be the number, capital X, because we use capital letters for random numbers, random variables. Let X be the number of people in the random sample of 100 people with brown eyes. So assuming that RH0 is true, so assuming that the proportion of brown-eyed people in the town is 80%, then the number of brown-eyed people in our sample of 100 is a binomial distribution with 100 trials, so 100 people in the sample, and a probability of success is 0.8. A two-tailed test means we split the significance level into two. Okay, so it's a two-tailed test, so we need to split 0.5% of the significance level into the lower tail of the distribution and 0.5% of the significance level into the upper tail of the distribution. If it was a one-tailed test, we don't need to do this. If it's a one-tailed test, all of the significance level is devoted to either the lower tail or the upper tail. If there's a less than sign here, then it would be dedicated to the lower tail. All your significance level would go to the lower tail. If it was a bit greater than sign here, all your significance level would go to the upper tail. So then using the calculator, we can obtain the following probability. So obviously in your exam, you don't, well, I say obviously, but it's maybe not obvious. When you write down your answers in the exams, we don't need to do all the work that I did on the previous slides where I listed out, where I guess lots of X numbers to go into the BCD function, the calculator, the binomial CD, I guessed a load of X numbers. I put in a load of numbers for X. We don't need to write that all down on our piece of paper in the exam. But what we do need to write down is the two key probabilities. So in this case, the probability, so we're going to put into a calculator X. So again, binomial CD, make sure we're in binomial CD with these hypothesis tests, binomial CD. X equals 69, number of trials 100, probability of success 0.8. If we execute that, press equals, we get this probability. So 0.006059. We did this before on the previous slide, by the way, the same calculation. And this is greater than 0.5%. So we'd write that down on the exam paper. And then again, I'm going to write down this on the exam paper as well. So the probability that we get less than or equal to 68 successes is 0.00313. So 0.313%, which is less than 0.5%. So this is where we have our little think. I'm going to stop a little bit. So we can see, right, that the critical region is going to be 68, 67, 66, 65, all the way up to 0. Okay, we can see that the critical region contains that. Now, remember, because we've actually done all the hard work before in the previous slides, we've also, this is going to be the lower tail critical region. Because it's a two-tail test, we're also going to have an upper tail critical region, but we don't actually need to worry about working that out in this exam question here. Again, remember, the reason why 69 is not in our critical region is because the probability we get 69 or less successes is bigger than the 0.5% significance level that we're devoting to the lower tail of the distribution. So it's a little bit too big, the probability. So John found, so if we remember what we said in the question on the previous slide. So John found that 67 people in the sample had brown eyes. Now, 67 people is in the critical region. 68 is in the critical region, 67, 66, 65, and so on and so on. 67 is a number in the critical region. So it is in the rejection region. So therefore, 67 is too far away from 80. Remember, we expect to get 80 successes, but actually we got 67 successes when we collected our data. 67 is too far, a little bit too far away. 60, sorry, I'm coughing there. Sorry about that. So 69 is a little bit too close to 80. So we would retain H0 if we've got 69 successes. If we got 68 successes, now we reject H0 because 68 is a little bit too far away from 80 successes. We actually got 67 successes, which is even further away. So because we found 67 successes, 67 being in the critical region means we need to reject H0. So this is our conclusion. The conclusion is that there is sufficient evidence to suggest that the proportion of people in the town with brown eyes is not 80%. So it's really important that you use this phrase here, there is sufficient evidence. So we're not proving these hypotheses. We can't prove, when you collect data and record data, we're not proving hypotheses. We can't prove these theories, right? We're not proving theories, right? We're collecting data and we're saying, does the data suggest one or the other theory? Does the evidence suggest we should go with one theory or the other theory? So you want to write this conclusion here. So there is sufficient evidence to suggest that the proportion of people in the town with brown eyes is not 80%. So remember, we have two theories. 80% is the proportion, 80% is not the proportion. So if we reject H0, we're going with this theory here. So we're going to write in words, and it's got to be in words. There is evidence to suggest that the proportion of people in the town with brown eyes is not 80%. So whatever this says here in your alternative hypothesis, not 80%, or it could be, so if it was a one-tail test, let's say it was a one-tail test, and your alternative hypothesis was P is greater than 0.8, then you'd write in your conclusion, there is evidence to suggest that the proportion of people in the town with brown eyes is greater than 80%. So you go with your alternative hypothesis, you follow that alternative hypothesis if you reject H0. Obviously, if you don't reject H0, if you accept H0, then you say that there is insufficient evidence to suggest the proportion is different from 80%. But because we're rejecting H0, because 67 people is in our critical region, it's in our rejection region, that means that there is sufficient evidence to suggest that the proportion of people in the town with brown eyes is not 80%, because 67 is too far away from the expected value of 80. And we know that because of these calculations here. these binomial distribution probability calculations that we can do on the calculator. So that's how I would structure an exam answer for this question here. So that's the end of today's video. So a very long video. And I just wanted to go through one kind of general example so you can kind of see the theory behind this. So hopefully this helps out. I know it's a very long video, but if you can follow step by step what we did, hopefully that does give you a little bit of help to understand a hypothesis test, to understand what hypothesis testing is all about, and understanding why we make certain conclusions. So thank you for watching. Please do like and subscribe to the channel. It really, really helps the channel. And please do share this with your friends. Share this with Year 12 students who are struggling with hypothesis testing. Or if you're a parent watching this and you know that your son or daughter or your child is struggling with hypothesis testing, then please do share this so they can watch this. So thank you very much for watching. I appreciate all the likes and people who subscribe to the channel. Thank you very much, and I'll see you guys all soon.